You have 15 seconds. That's how long you'd survive on Mars without a spacesuit before unconsciousness. 2 minutes until death. Think that sounds bad? That's the least of your problems. Mars isn't just hostile, it's a perfectly designed death trap operating on a planetary scale. And here is a question. If you could choose one challenge to solve first for Mars colonization, which would you pick and why? Comment down below. I'll pin the most creative answer. Now let's begin. Here's what's happening above your head every single second on Mars. Galactic cosmic rays, or GCR for short, are screaming toward the planet at nearly the speed of light. These aren't just particles, they're the shredded remains of exploded stars accelerated across the galaxy to unimaginable velocities. About 89% are protons, 10% are helium nuclei, and 1% are heavier nuclei, some of them carrying more energy than a professional baseball pitcher throws into a fastball. Except these particles are smaller than an atom. On Earth, we're protected. Our planet's magnetic field acts like an invisible shield, deflecting most of this cosmic artillery. The atmosphere provides another layer of defense, absorbing what gets through. But Mars lost its global magnetic field billions of years ago. Its atmosphere is less than 1% the thickness of Earth's. There's almost nothing standing between you and the universe's radiation. The numbers are genuinely frightening. According to measurements from NASA's Radiation Assessment Detector aboard the Curiosity rover, astronauts on the Martian surface would receive approximately 600 to 700 millisieverts of radiation per year. To put that in perspective, the annual limit for radiation workers on Earth is just 50 millisieverts. A single year on Mars exposes you to more than a dozen times what we consider safe here at home. But it gets worse. The journey to Mars itself is even more dangerous. During the 6 to 9 month voyage through deep space, you'd be completely exposed to cosmic radiation without even the thin protection Mars's atmosphere provides. NASA scientists estimate that astronauts traveling to Mars and back would accumulate effective doses exceeding 1,000 millisieverts. That level of exposure dramatically increases your lifetime cancer risk, potentially by 5 to 10% or more. Now, before you think, well, that's just cancer risk down the road, let me introduce you to something even more immediate and terrifying: solar particle events, or SPEs. These are massive eruptions from the Sun that hurl billions of tons of charged particles into space at millions of miles per hour. When one of these storms hits, radiation levels can spike to lethal doses within hours. Imagine you're exploring a crater 20 miles from your base when sensors detect an incoming solar storm. You have maybe 30 minutes to get back to shelter before radiation levels become fatal. There's no speeding home in your rover because Martian terrain is treacherous, filled with rocks, cliffs, and dusty slopes. Every second counts, and there's nowhere to hide on the surface. This isn't theoretical. Solar particle events happen multiple times per solar cycle, which lasts approximately 11 years. During the Apollo missions to the Moon, astronauts were incredibly fortunate that no major solar storms occurred during their brief surface excursions. A Mars mission lasting months or years, the odds aren't in your favor. The biological damage from this radiation is profound. Unlike the relatively low-energy radiation from X-rays or even nuclear accidents on Earth, cosmic rays include high-charge, high-energy nuclei that tear through cells like microscopic bullets. When a single iron nucleus traveling at 98% the speed of light passes through your brain, it doesn't just damage one cell. It creates a track of destruction, shattering DNA strands, generating free radicals, and potentially killing dozens of cells along its path. Recent studies published in 2026 reveal something even more disturbing. This type of radiation doesn't just increase cancer risk, It can cause circulatory diseases, accelerate aging, and potentially damage the central nervous system in ways we're only beginning to comprehend. Researchers found that exposure to galactic cosmic rays might impair cognitive function, affecting memory, decision-making, and reaction times. On a planet where a single mistake could cost your life, having your mental sharpness degraded by radiation is a death sentence waiting to happen. Scientists have proposed various shielding strategies. You could bury habitats under several feet of Martian soil, which would absorb much of the radiation. You could design spacecraft with water-filled walls, using the hydrogen atoms to block particles. Some researchers even suggest creating artificial magnetic fields around habitats. But here's the problem. Every solution adds massive weight, complexity, and cost, and none of them provide complete protection. There's also the haunting reality that we simply don't know the full extent of what decades of cosmic radiation exposure will do to the human body. Our data comes from astronauts who've spent months in low Earth orbit, protected by Earth's magnetic field, or from radiation therapy patients exposed to different types of radiation. Sending humans to Mars means conducting an experiment we've never done before, using astronauts as test subjects in an environment where medical evacuation is impossible. Think about that for a moment. If an astronaut on the International Space Station develops a serious medical condition, they can be home within hours. On Mars, you're a minimum of 6 months away from Earth, and that's only when the planets align favorably. Most of the time, you're looking at 9 months or longer. There's no coming home if something goes wrong. There's no emergency room, no specialized surgeons, no advanced medical equipment beyond what you brought with you. This brings us to an uncomfortable truth that mission planners discuss behind closed doors. NASA's current radiation exposure limits state that astronauts cannot exceed a 3% increase in lifetime fatal cancer risk. Based on current models, a round-trip Mars mission would likely exceed that limit, possibly reaching 5 to 10% or higher when you account for uncertainties in the biological effects of cosmic radiation. And here's where I want you to truly grasp the magnitude of what we're discussing. That 3% limit, it's not just a number pulled from thin air. It represents a moral and ethical boundary, a line we've drawn saying, we will not ask astronauts to take risks beyond this point. A Mars mission doesn't just approach that line, it potentially leaps over it, landing in territory where we're asking human beings to accept significant risks of dying from radiation-induced illness years or decades after their mission ends. If you're finding this exploration of space's harsh realities as fascinating as I do, please give this video a like. Your support genuinely makes a difference. Now, let's say you've somehow solved the radiation problem. You've got incredible shielding, maybe even some future medical treatment that repairs radiation damage. You're feeling pretty good about your chances on Mars. That's when the planet reveals its second secret weapon. The soil itself is trying to poison you. In 2008, NASA's Phoenix lander made a discovery that changed everything we thought we knew about Martian soil. It found perchlorate, a toxic chemical compound, mixed throughout the dirt at concentrations of about 0.5% to 1%. That might not sound like much, but it's actually staggering. Imagine Earth's soil containing that much of a substance that interferes with your thyroid function, disrupts your endocrine system, and can cause serious developmental problems. Perchlorate on Mars isn't just in one location. Subsequent missions, including Curiosity and Perseverance, have confirmed its presence across different regions of the planet. It's everywhere, mixed into the fine dust that covers everything, waiting to contaminate your equipment, your habitat, and potentially your body. Here's why this matters so much. Mars is dusty, incredibly dusty. When astronauts walked on the moon, lunar dust got into everything despite their best efforts to keep it out. It clung to their suits using static electricity, infiltrated airlocks, and caused mechanical problems with equipment. Martian dust will behave similarly, except unlike lunar dust, it's chemically toxic. Every time you come back inside from a surface excursion, you're potentially bringing perchlorate into your living space. It could contaminate your water recycling systems, get into your food production areas, or become airborne and inhaled. The Agency for Toxic Substances and Disease Registry lists perchlorate as a chemical that can interfere with thyroid hormone production, which regulates metabolism, growth, and development. Chronic exposure could lead to thyroid problems, hormonal imbalances, and other health issues that would be extremely difficult to treat millions of miles from Earth. But wait, there's more. Scientists conducting experiments to understand how perchlorate behaves on Mars made a chilling discovery. When perchlorate is exposed to the intense radiation on Mars, something terrifying happens. It breaks down into even more reactive compounds, including hypochlorite, chlorine dioxide, and trapped oxygen molecules. These breakdown products are incredibly reactive. Hypochlorite is the active ingredient in bleach. Let that sink in for a moment. The Martian soil, when bombarded by cosmic radiation for billions of years, has essentially become mixed with bleach-like compounds. This explains one of the greatest mysteries from the Viking lander missions in the 1970s, when Viking conducted biology experiments, mixing Martian soil with nutrients to look for signs of microbial life. Something bizarre happened. The soil reacted violently, releasing oxygen and destroying organic molecules. For decades, scientists debated what could cause such reactivity. Now we know. The combination of perchlorate and radiation created a cocktail of oxidizing chemicals that essentially sterilizes the surface, breaking down any organic compounds it encounters. This has profound implications for human survival. If you want to grow food on Mars, you can't just scoop up dirt and plant seeds like Matt Damon did in The Martian. The soil would literally attack your plants at a chemical level. You'd need to extensively process the regolith, removing or neutralizing the perchlorate and its byproducts before anything could grow. That means bringing or building sophisticated chemical processing equipment, using precious water and energy to wash the soil, and somehow disposing of the toxic waste you create. Some researchers have proposed using bacteria that can actually consume perchlorate, breaking it down into harmless chloride and oxygen. In fact, studies published in 2026 showed that certain beneficial fungi could potentially help convert Martian regolith into biologically friendly soil for crops. It's a fascinating solution, but it adds another layer of complexity to an already impossibly complex mission. You'd essentially need to establish a biological remediation system, carefully managing microbial cultures while simultaneously trying not to die from a dozen other threats. There's also the question of where you get your water. Mars has water ice, substantial amounts of it, locked in the polar caps and scattered in deposits across the planet. Sounds great, right? Wrong. That ice is mixed with, you guessed it, perchlorate. Data from NASA's Phoenix lander and subsequent missions confirmed that Martian ice contains significant concentrations of this toxic salt. Before you can drink that water, use it to grow food, or even use it for hygiene, you need to purify it, removing chemicals that could poison you. Every single system on Mars becomes interconnected in ways that create cascading failure points. Contaminated soil means you need water purification. Water purification requires energy. Energy generation requires equipment that must be protected from dust. Dust contains perchlorate. See the problem? It's not just about solving individual challenges. It's about creating a completely closed-loop life support system where nothing can fail, because if one component breaks down, it threatens everything else. And we haven't even discussed the psychological challenges yet. Let's talk about what Mars does to your mind, because in many ways, this might be the most terrifying aspect of all. Picture this. You're living in a habitat the size of a small house with maybe 5 other people. Outside, the landscape is barren, rust-colored rocks and dust extending to the horizon in every direction. The sky is a butterscotch hue, thin and offering no real protection. You can't go outside without a spacesuit. You can't open a window for fresh air. You can't take a walk in nature. You can't escape your crewmates for more than a few minutes. And you're going to live like this for at least 2 years, possibly longer. Communication with Earth takes between 4 and 24 minutes one way, depending on where Mars is in its orbit. That means no real-time conversations with loved ones. No calling home when you're having a bad day to hear a familiar voice immediately respond. Every message you send takes minutes to arrive, and the response takes just as long to come back. In psychological terms, you're more isolated than any human being has ever been in history. Research from Antarctic winter-over cruise, submarine missions, and the International Space Station has given us glimpses into what this kind of isolation does to people. Crews experience something called the third quarter phenomenon, where psychological issues peak about 70 to 75% through a long-duration mission. People become irritable, depressed, and sometimes hostile. Sleep patterns deteriorate, performance declines, and that's with the knowledge that rescue is possible if things go catastrophically wrong. On Mars, rescue isn't possible. If your crew develops severe interpersonal conflict, you can't separate them. If someone experiences a psychological breakdown, you don't have mental health professionals beyond whatever training the crew received. If somebody makes a catastrophic decision due to impaired judgment, there's no backup team to intervene. You're absolutely, utterly on your own. Recent studies on the effects of cosmic radiation on the brain add another horrifying dimension to this. Research indicates that exposure to high-energy particles can cause inflammation in brain tissue, potentially affecting mood regulation, decision-making, and impulse control. Imagine trying to maintain psychological stability while the radiation bombarding your brain is literally changing how your neurons function. It's like fighting a battle on 2 fronts: the external stress of the environment and the internal stress of your brain chemistry being altered by forces beyond your control. There's also sensory deprivation to consider. Mars provides a monotonous environment. The same reddish landscape every day. No rain, no seasons in the way we experience them on Earth, no forests or oceans or any of the natural diversity our brains evolved to process. Humans need environmental stimulation. We need variety, nature, and connection to the living world. Mars offers none of that. It's a dead planet, and living there means surrounding yourself with lifelessness every single day. Some mission planners suggest bringing virtual reality systems, large video screens displaying Earth scenes, even recorded nature sounds to provide psychological comfort. But can simulated experiences truly replace the real thing for years on end? We don't know because we've never tried. Mars astronauts will be the first to find out, and the cost of getting it wrong isn't just discomfort. It's potential mission failure, crew safety incidents, or psychological trauma that could last a lifetime. Let me paint an even darker picture for you. Imagine an emergency situation arises. Maybe a critical system fails. Maybe someone gets injured. On Earth, in a crisis, your body floods with adrenaline, your heart rate increases, and you move quickly to respond. But on Mars, you're wearing a bulky spacesuit that restricts your movement. Every action takes longer. You can't see as well through your helmet visor. You can't hear as clearly. Your fine motor control is limited by thick gloves. And all of this is happening while you're trying to solve a problem that could kill you and everyone else in the habitat if you fail. The combination of chronic stress, isolation, radiation exposure affecting cognition, and the constant threat of equipment failure creates a psychological pressure cooker unlike anything humans have experienced. Antarctic researchers report that some winter-over crew members develop something called expedition syndrome, characterized by irritability, depression, and cognitive impairment. Now multiply that by the fact that you're not just in Antarctica. You're on another planet where the environment is actively trying to kill you every second of every day. Here's something most people never consider: boredom. Yes, boredom on Mars. You might think being on another planet would be endlessly exciting, but the reality is that most of your time would be spent on routine maintenance, scientific experiments, and exercise to prevent muscle and bone loss. Days would blend together in a monotonous routine designed to keep you alive. The thrill of being on Mars would likely wear off after a few weeks, leaving you with months or years of grinding sameness. Astronauts need approximately 2.5 hours of exercise every day just to counteract the muscle atrophy and bone density loss from reduced gravity. Mars has about 38% of Earth's gravity, which sounds better than zero gravity on the International Space Station, but it's still enough to cause significant physiological changes over time. Your muscles would weaken, your bones would lose calcium, your cardiovascular system would adapt to the lower gravity in ways that might make returning to Earth extremely difficult or even dangerous. Speaking of gravity, let's explore what 3/8 Earth gravity does to your body over months and years. We have extensive data from astronauts in microgravity, and we know Earth's full gravity intimately, but that middle zone? That's largely unknown territory. Scientists call it a knowledge gap, which is a polite way of saying we're going to find out what happens by sending people there and hoping for the best. In microgravity, astronauts lose approximately 1 to 2% of bone mass per month in weight-bearing bones. The reduced gravity on Mars would slow that loss, but not stop it. Over a 2 or 3 year mission, you could lose significant bone density, increasing your risk of fractures. And remember, a broken bone on Mars isn't just painful, it's potentially life-threatening because your medical resources are extremely limited. Your inner ear, which controls balance, would also adapt to the reduced gravity. When you eventually return to Earth, you might have severe difficulty walking, standing, or even sitting up without dizziness. Astronauts returning from 6-month stays on the International Space Station often need assistance just to walk and require weeks or months of rehabilitation. Mars astronauts might need even longer recovery periods, and there's a genuine possibility that some physiological changes could be permanent. The human spine elongates in reduced gravity as the vertebrae spread apart without full body weight compressing them. This causes back pain for many astronauts and can lead to nerve impingement. Imagine dealing with chronic back pain while simultaneously managing all the other stresses of living on Mars. There's no taking a day off to rest. There's no visiting a chiropractor. You either push through the pain or compromise mission objectives. Your eyes would also change. Astronauts in microgravity often experience vision problems due to fluid shifts that increase pressure inside the skull, affecting the optic nerve and eyeball shape. This condition, called spaceflight-associated neuroocular syndrome, or SANS, affects more than half of astronauts on long-duration missions. The reduced gravity on Mars might lessen this effect compared to microgravity, but we simply don't know how much. What if you're the mission pilot and your vision starts deteriorating? What if you're the medical officer and you can't see clearly to perform emergency procedures? Let's talk about something you probably haven't considered: your immune system. Research from the International Space Station shows that spaceflight significantly weakens immune function. Radiation exposure damages immune cells. Stress hormones suppress immune responses. Disrupted sleep patterns, which are common in space due to altered light-dark cycles and psychological stress, further impair your body's ability to fight infections. On Mars, you're dealing with all of these immune-suppressing factors simultaneously. Now imagine a crew member develops an infection. Even a simple bacterial infection could become life-threatening if your immune system isn't functioning properly and your antibiotic supplies are limited. We haven't even considered the possibility of unknown Martian microbes, which most scientists believe are unlikely but not impossible. If life ever existed on Mars and somehow still persists in subsurface environments, could it pose a biological hazard? We genuinely don't know. The harsh reality is that Mars offers no forgiveness for mistakes, no second chances when systems fail, and no evacuation route when things go catastrophically wrong. Every single decision carries weight that's difficult to comprehend from the safety of Earth, and we're just getting started on understanding the full scope of challenges awaiting anyone brave or perhaps foolish enough to attempt living there. Let's shift our focus to something seemingly mundane but absolutely critical: air. You need to breathe, obviously, but Mars's atmosphere is 95% carbon dioxide with less than 1% oxygen. The atmospheric pressure at the surface is about 0.6% of Earth's pressure at sea level. That's equivalent to being at an altitude of about 100,000 feet on Earth, roughly 3 times higher than commercial airplanes fly. What happens if you step outside without a spacesuit? First, the lack of pressure would cause the water in your tissues to vaporize. Your body wouldn't explode like in the movies, but you'd swell up painfully as dissolved gases in your blood formed bubbles. Within 15 seconds, you'd lose consciousness from oxygen deprivation. Your lungs would be damaged from trying to breathe in an atmosphere that's essentially a vacuum. Within 2 minutes, you'd be dead. It wouldn't be dramatic. It would be quick, painful, and absolutely final. This means every single excursion outside requires a fully functional spacesuit, which is essentially a personal spacecraft that provides pressure, oxygen, temperature control, and radiation protection. These suits are complex pieces of equipment with thousands of components, any of which could potentially fail. On Earth, astronauts have extensive support teams monitoring suit telemetry, ready to assist if problems arise. On Mars, you're largely on your own. Spacesuits also have limited operational lifetimes. They degrade with use, seals wear out, fabrics tear, joints stiffen. During the Apollo missions, which lasted only days on the lunar surface, astronauts reported significant dust infiltration and mechanical issues with their suits. A Mars mission lasting months means your suits will need constant maintenance and repair, which requires spare parts, tools, and expertise. What happens when a critical component breaks and you don't have a replacement? There's also the question of how you produce breathable air inside your habitat. You can't bring enough oxygen from Earth for a multi-year mission. You need to generate it on Mars, which means either extracting it from the Martian atmosphere or breaking down water through electrolysis. NASA's Perseverance rover carried an experiment called MOXIE, the Mars Oxygen in Situ Resource Utilization Experiment, which successfully demonstrated converting carbon dioxide into oxygen. That's genuinely exciting progress. But scaling up from a small experimental device to a system that produces enough oxygen for multiple humans continuously is an enormous engineering challenge. You'd also need backup systems, because a single point of failure in your oxygen generation means everyone dies within hours. Triple redundancy might sound excessive, but on Mars, it's the bare minimum for survival. Every backup system adds weight, complexity, and more components that could potentially malfunction. The engineering required is staggering, and it all needs to function perfectly, continuously, for years, without access to replacement parts beyond what you brought with you. Water presents similar challenges. Humans need approximately 2 to 3 liters of drinking water per day, plus additional water for hygiene, growing food, and industrial processes. You absolutely cannot bring enough water from Earth for a multi-year mission. You must extract it from Mars, likely from subsurface ice deposits. But mining ice on Mars isn't like scooping snow on Earth. You need drilling equipment that can penetrate frozen ground in sub-zero temperatures. You need heating systems to melt the ice. You need purification systems to remove perchlorate and other contaminants, and you need to do all of this while managing your energy budget carefully. Energy is the lifeblood of everything on Mars. Without it, your oxygen generation stops, your water purification stops, your heating stops, your communication with Earth stops. Everything stops, and everyone dies. Solar panels seem like an obvious solution, but Martian dust storms can block sunlight for weeks or even months at a time. In 2018, a planet-wide dust storm caused NASA's Opportunity rover to lose power, and the rover never recovered. Solar panels alone aren't reliable enough for human survival. Nuclear power sources, specifically radioisotope thermoelectric generators or small nuclear reactors, offer more consistent energy production. Curiosity and Perseverance rovers both use plutonium-based power systems that work regardless of dust storms or time of day. Scaling that technology up for human missions is feasible, but presents its own challenges. You're essentially placing a nuclear reactor near your living quarters, which requires extensive shielding, safety systems, and waste heat management. The irony isn't lost on anyone. You go to Mars to escape one radiation source and end up living next to another. Let's talk about food, because you can't survive on freeze-dried meals for 2 or 3 years without serious nutritional deficiencies and psychological consequences. Astronauts need approximately 2,000 to 2,500 calories per day, along with proper vitamins, minerals, and variety to maintain physical and mental health. That means you either bring all your food from Earth, which requires massive cargo capacity, or you grow it on Mars. Growing food on another planet sounds romantic until you examine the details. Plants need light, water, nutrients, appropriate temperature, and atmosphere with carbon dioxide. Mars provides plenty of carbon dioxide, but that's about it. You'd need to build pressurized greenhouses, provide artificial lighting or concentrate sunlight, heat the space to temperatures plants can tolerate, provide water without perchlorate contamination, and create soil that isn't toxic to plant life. Research published in 2026 demonstrated that maize, a staple crop, could potentially survive on Mars, but only after extensive soil remediation to remove toxic compounds. The study found that the chemical composition of Martian regolith was a far greater threat to plant survival than reduced gravity or the lack of magnetic field. This means you can't just set up a greenhouse and start farming. You need industrial-scale soil processing before a single seed can germinate successfully. There's also the problem of pollination. Many crops require pollination by insects or wind, neither of which exist on Mars. You'd need to either manually pollinate plants, which is incredibly time-consuming, or bring pollinating insects, which creates another biological system requiring management and care. Bees don't just need flowers, they need appropriate temperature, humidity, and space to build hives. Managing an insect colony while trying not to die on Mars adds yet another layer of complexity to an already overwhelming challenge. Crop failures would be catastrophic. On Earth, if your garden dies, you go to the grocery store. On Mars, if your crops fail, you starve. There's no resupply mission that can reach you in time to prevent malnutrition or starvation. You'd need multiple redundant food production systems, extensive seed banks, and probably several years' worth of emergency rations just in case everything goes wrong simultaneously. Let's examine the habitat itself, the structure you'd live inside. It needs to provide pressure, protection from radiation, temperature control, and enough space for humans to live without going insane. The habitat would likely be partially buried under Martian regolith for radiation shielding, which means you're essentially living underground. Windows would be small and heavily shielded if they exist at all. Natural light would be minimal. You'd spend most of your time in artificial lighting, which further disrupts your circadian rhythms and adds to the psychological burden. The habitat also needs to maintain structural integrity despite temperature swings of over 100 degrees Celsius between day and night. Materials expand and contract with temperature changes, creating stress on seals and joints. A tiny crack in the habitat's pressure vessel could lead to catastrophic decompression. Regular inspections and maintenance would be essential, but how do you thoroughly inspect a structure that's buried under several feet of dirt? Fire is another terrifying consideration. In a pressurized habitat filled with oxygen, fire spreads rapidly and produces toxic smoke. You can't just open a window to vent the smoke. You can't evacuate outside without spacesuits, which take time to put on. Fires on spacecraft and in enclosed habitats are extremely dangerous, and fighting them requires specialized equipment and training. The Apollo 1 tragedy, where 3 astronauts died in a cabin fire during a ground test, serves as a sobering reminder of how quickly disaster can strike in oxygen-rich environments. Equipment failures are inevitable over a multi-year mission. Things break, especially in extreme environments. Martian temperatures average around -63 degrees Celsius, cold enough to make metals brittle and plastics crack. Dust infiltrates moving parts, causing wear and malfunction. Radiation damages electronic components over time. You'd need extensive spare parts, sophisticated diagnostic tools, and crew members skilled enough to repair virtually any system that could fail. But here's the catch. You can't bring infinite spare parts. Every kilogram launched to Mars costs thousands of dollars and requires fuel, which adds more weight. Mission planners must carefully calculate what to bring based on statistical failure rates, but statistics don't care about your planning. If a critical component fails and you don't have a spare, you either improvise a repair using whatever materials you have or face potentially mission-ending consequences. 3D printing technology offers some hope here. If you can bring raw materials and a sophisticated enough printer, you might be able to manufacture replacement parts on demand. NASA has tested 3D printing on the International Space Station with promising results. But Martian conditions are far harsher than low Earth orbit. Printers would need to function in reduced gravity, possibly in temperature extremes, and produce parts with the same reliability as Earth-manufactured components. One improperly printed seal or valve could lead to catastrophic failure. Communication delays create another dimension of isolation and danger. When Mars is closest to Earth, radio signals take approximately 4 minutes to travel between planets. When Mars is on the opposite side of the Sun from Earth, that delay increases to around 24 minutes. This means every conversation with mission control involves waiting at least 8 to 48 minutes for a response. You can't have a real-time discussion about an emergency. You can't ask for immediate guidance when facing a critical decision. Astronauts on Mars would need to be far more autonomous than any previous space explorers. They'd need expertise in engineering, medicine, geology, biology, chemistry, and psychology. They'd need to diagnose and solve problems independently, because waiting nearly an hour for advice from Earth could mean the difference between life and death. The crew selection process would be incredibly stringent, looking for individuals with not just technical skills, but also emotional stability, adaptability, and the ability to function under prolonged extreme stress. Training for a Mars mission would likely take years, making the overall time commitment immense. You might spend 5 years training, 3 years on the mission including travel time, and then months or years recovering after return. That's potentially a decade of your life dedicated to a single mission with significant health risks and no guarantee of success. Who volunteers for that? What kind of person looks at those odds and says, "Yes, I want to go"? History suggests there will be volunteers. Humans have always pushed boundaries, explored dangerous frontiers, and risked everything for discovery and adventure. But the ethical questions surrounding Mars missions are profound. Is it morally acceptable to send people on a mission where the risk of death or permanent injury is so high? How do we balance the scientific and inspirational value of human Mars exploration against the very real possibility that we're sending people to their deaths? These aren't abstract philosophical questions. They're practical considerations that space agencies, governments, and the astronauts themselves must grapple with. NASA's current risk tolerance limits exist for a reason, and a Mars mission pushes or exceeds those limits. We're entering territory where we're asking human beings to accept risks that we've previously deemed unacceptable. That's a sobering reality that deserves serious reflection. Let's dig deeper into the medical challenges, because they're truly nightmare-inducing. Imagine you're millions of miles from the nearest hospital and you develop appendicitis. On Earth, this is a routine emergency requiring surgery within hours to prevent the appendix from rupturing and causing potentially fatal peritonitis. On Mars, you don't have a surgeon. You might have a crew member with medical training, but they're not a specialist. You don't have a fully equipped operating room. You have whatever medical supplies were packed into the habitat. The crew would need to perform emergency surgery using telemedicine guidance from Earth. But remember those communication delays. By the time you describe symptoms to mission control and they respond with advice, your condition could have worsened significantly. Medical emergencies don't wait for convenient communication windows. They happen suddenly, progress rapidly, and demand immediate intervention. Medical supplies have limited shelf lives. Medications degrade over time, especially when exposed to radiation. A 3-year mission means some of your pharmaceutical supplies might lose effectiveness before you need them. You can't just reorder prescriptions or pop down to a pharmacy. Whatever you brought is all you have, and if critical medications become ineffective, you're facing medical crises with inadequate tools. Dental emergencies present another horrifying scenario. A severe toothache, an abscess, or a broken tooth might seem minor compared to other threats, but dental pain can be absolutely debilitating. Without a dentist, treating dental emergencies means either suffering through excruciating pain or having a crew member attempt dental procedures with minimal training and equipment. Imagine trying to extract an infected tooth on another planet using whatever tools you have available. It's a scene from a horror movie, except it's a real possibility. Surgical complications are even worse. What if someone needs surgery and develops an infection afterward? What if there's internal bleeding that doesn't stop? What if someone has an allergic reaction to anesthesia? On Earth, these complications are managed by specialists with extensive resources. On Mars, you're improvising with limited supplies and hoping for the best. The mortality rate for medical emergencies on Mars would likely be significantly higher than on Earth, simply due to resource limitations. Mental health crises could be equally dangerous. Depression, anxiety, and acute stress reactions are almost guaranteed on a long-duration Mars mission. Most of these can be managed with counseling, medication, and support. But what about severe psychiatric emergencies? What if someone becomes actively suicidal or psychotic? You can't hospitalize them. You can't separate them from the crew for extended periods. You need everyone to maintain the habitat and survive. Psychiatric medications also have side effects that might be problematic in a survival environment. Antidepressants can cause drowsiness, affecting reaction times. Anti-anxiety medications might impair judgment, yet withholding treatment could lead to even worse outcomes. It's a delicate balance with no easy answers, and the psychological screening before the mission, no matter how rigorous, can't predict with certainty how someone will respond to years of isolation and stress. Now let's talk about something that might sound trivial, but is actually crucial: waste management. Humans produce waste, both biological and material, and on Mars you can't just throw it away. There's no away. Everything stays with you unless you develop systems to process, recycle, or safely dispose of it. Human waste contains valuable resources, primarily water and nutrients that could be used for agriculture. The International Space Station recycles urine into drinking water, a process that sounds disgusting but is scientifically sound and highly efficient. On Mars, you'd need similar systems, but scaled up and designed for long-term reliability. These systems can't fail because you need every drop of water you can recover. Solid waste presents different challenges. You could potentially use it as fertilizer after appropriate processing to kill pathogens. But remember, you're also dealing with potential chemical contamination from medications in the waste stream. You'd need careful management to avoid introducing harmful substances into your food production systems. The engineering required to create a completely closed-loop waste processing system is incredibly complex. Non-biological waste like broken equipment, packaging materials, and worn-out components also accumulates. You can't let it pile up indefinitely inside the habitat. You could dump it outside, creating a garbage heap on pristine Martian landscape, but that raises planetary protection concerns. We have international agreements about contaminating other worlds. Plus, some of that waste might contain materials you'll eventually need to reuse or recycle. Recycling on Mars is fundamentally different from recycling on Earth. You're not just doing it for environmental reasons, you're doing it for survival. Every piece of metal, every bit of plastic, every scrap of fabric could potentially be repurposed into something you desperately need later. You'd need to catalog everything, store it appropriately, and have the tools and knowledge to transform waste materials into useful items. It's like living in a permanent survival situation where nothing can be wasted. The sheer amount of planning required is staggering. Every single item brought to Mars must be carefully selected based on multiple criteria: mass, utility, durability, repairability, and versatility. Mission planners must think through scenarios years in advance, anticipating needs and problems that might arise. Despite the best planning, Unexpected situations will occur. That's where human ingenuity becomes the most critical resource, and also the most unpredictable factor. Let's explore the journey to Mars itself, because even getting there is terrifying. The transit takes 6 to 9 months, depending on the trajectory and propulsion technology. That's half a year to 9 months confined in a spacecraft that's essentially a tin hurtling through the void of space. The spacecraft would be cramped with minimal privacy and no escape from your crewmates. During this journey, you're exposed to the full intensity of cosmic radiation and solar particle events without any planetary protection whatsoever. The spacecraft would have some shielding, but as mentioned earlier, effective shielding adds massive weight. There's a trade-off between protection and the fuel required to accelerate that mass to Mars, and typically, fuel considerations win. You accept higher radiation exposure to make the mission possible at all. Microgravity during the transit causes all the physiological problems we discussed earlier. Bone loss, muscle atrophy, fluid shifts, vision changes, and immune system suppression. By the time you arrive at Mars, you're already physically weakened. Then you need to immediately begin working in a hostile environment, setting up habitats, conducting experiments, and establishing life support systems. There's no recovery period. You hit the ground running, literally, except your bones are weaker and your muscles have atrophied. The landing itself is another moment of sheer terror. Mars has enough atmosphere to create heating during entry, but not enough to slow you down significantly with parachutes alone. You need a combination of heat shields, parachutes, and retro rockets to land safely. Every Mars landing is described by engineers as 7 minutes of terror, the time between entering the atmosphere and touching down. During those 7 minutes, everything must work perfectly or you crash. Unlike robotic missions, where a failure means loss of equipment and scientific disappointment, a crewed landing failure means human deaths. The stakes are incomparably higher. Every system must be tested exhaustively, with redundancies and backup plans, but ultimately, you're still dropping a spacecraft carrying humans onto another planet, using technology that's only been tested with robots. The first crewed Mars landing will be one of the most dangerous moments in human history. Assuming you survive the landing, you then face the challenge of immediate habitat setup. You can't live in the spacecraft indefinitely. You need to deploy or construct a habitat, connect power systems, establish life support, and make the environment livable, all while wearing spacesuits and working in an alien environment. Every task takes longer than it would on Earth. Everything is harder. Fatigue sets in quickly. Mistakes become more likely precisely when you can least afford them. Early Mars missions will likely use pre-deployed cargo missions, where habitats and supplies are sent ahead of the crew and set up robotically or await crew arrival. This reduces some risks, but it also means you're depending on systems that have been sitting on Mars, exposed to dust, temperature extremes, and radiation, possibly for months or years before you arrive. What if something failed during that time? What if dust covered solar panels or damaged seals? You won't know until you get there. The return journey presents its own unique terrors. You need to launch from Mars, which requires a rocket and fuel. That fuel either needs to be brought from Earth, which is incredibly heavy, or produced on Mars using local resources, which requires additional equipment and time. The concept is called In Situ Resource Utilization, or ISRU, and it's essential for making Mars missions feasible. But it's also unproven at the scale required for a crewed rare turn. Imagine the scenario. You're ready to come home after years on Mars, exhausted, physically weakened, psychologically strained. You climb into the ascent vehicle and initiate the launch sequence. The engines ignite, and you begin to lift off. Everything needs to work perfectly. There are no second chances. If the ascent vehicle fails, you're stranded on Mars with no possibility of rescue. You'll die there, millions of miles from home, and everyone on Earth will watch helplessly as your life support eventually runs out. Even if the launch succeeds, you then face another 6 to 9 months in space, this time even more weakened from your time on Mars. Your body has adapted to Martian gravity, and now you're back in microgravity, which causes another round of physiological stress. You might arrive back at Earth in such weakened condition that the re-entry and landing pose serious health risks. Re-entry to Earth is violent. You're hitting the atmosphere at thousands of miles per hour, experiencing multiple Gs of deceleration with extreme heat from atmospheric friction. Astronauts in prime physical condition find it challenging. Astronauts who've spent years in reduced gravity and microgravity might find it dangerous or even potentially fatal. Their hearts might not handle the stress. Their weakened bodies might not withstand the forces involved. If you survive re-entry and landing, you then face months of rehabilitation, relearning how to walk in Earth's gravity, rebuilding muscle and bone, and dealing with potential long-term health consequences from radiation exposure. Some effects might not appear for years or decades: cancer, cardiovascular disease, neurological problems. These could all manifest long after the mission ends, turning Mars astronauts into medical case studies for the rest of their lives. The long-term health monitoring required for returned Mars astronauts would be extensive and lifelong. Every medical issue, every symptom, every diagnosis becomes data for understanding what extended exposure to the Martian environment does to human biology. In a very real sense, Mars astronauts are volunteers for an experiment where they themselves are the test subjects, and the results won't be fully known until decades after the mission concludes. Let's examine dust storms more closely, because they're far more dangerous than most people realize. Martian dust storms can grow to planetary scale, engulfing the entire world in a reddish haze that blocks out the sun for weeks or even months. The storm that killed NASA's Opportunity rover in 2018 lasted for months, covering the planet in darkness that prevented the solar-powered rover from recharging its batteries. For human missions, a global dust storm presents cascading problems. Solar panels become useless, covered in dust and deprived of sunlight. If you're depending on solar power, your energy production drops to nearly zero. Battery reserves drain quickly when you're supporting life support systems, heating, and essential operations. If you don't have nuclear power or sufficient battery capacity, you could run out of power before the storm clears. Temperature drops significantly during dust storms because sunlight can't reach the surface. You need more energy for heating precisely when your power generation is compromised. It's a vicious cycle that could prove fatal. Even with nuclear power providing baseline energy, the extreme cold and reduced visibility make external activities impossible. You're trapped inside, unable to conduct maintenance, gather resources, or address problems that might be developing outside. Dust itself is incredibly fine on Mars, much finer than most sand on Earth. It's electrostatically charged, clinging to everything it touches. This dust can damage equipment, infiltrate seals, scratch visors, and clog filters. During Apollo missions, lunar dust caused significant problems despite the missions being only days long. Martian dust over years would be exponentially worse. Managing dust contamination would be a constant, exhausting battle that you can never truly win. The dust particles are also sharp at the microscopic level, with jagged edges that can damage lung tissue if inhaled. Your habitat's air filtration systems need to be absolutely perfect because even small amounts of Martian dust getting into your breathing air could cause serious respiratory problems over time. There's no replacing damaged lungs on Mars. Once they're scarred, you're dealing with permanent respiratory impairment. Some researchers have raised concerns about the potential toxicity of Martian dust beyond just the perchlorate content. The fine particles might cause inflammation similar to silicosis, a lung disease caused by inhaling crystalline silica dust. We won't know for certain until humans are actually exposed, which is a terrifying prospect. You're essentially finding out whether the dust is toxic by breathing it and hoping you don't develop chronic lung disease millions of miles from medical care. Now let's discuss something that sounds almost absurd given all the other dangers: the possibility of accidents. Humans have accidents. We trip, we fall, we make mistakes. On Earth, most accidents are minor. You might break an arm, sprain an ankle, or get a cut that requires stitches. On Mars, those same accidents could be fatal. Falling in a spacesuit could damage the suit's integrity, causing a pressure leak. Even a small tear could be catastrophic if you're far from the habitat. You'd have minutes at most to patch the leak or reach safety before you lose consciousness from oxygen deprivation. And remember, you're in a bulky suit with limited mobility, making it harder to react quickly to emergencies. A broken bone during a surface excursion presents enormous challenges. You need to get back to the habitat, which might be miles away, while in severe pain and with compromised mobility. Your crewmates would need to help you, but that puts additional strain on everyone and increases risk. Once back at the habitat, that broken bone needs to be set and immobilized, a painful procedure even with proper medical care, let alone with limited supplies and training. Head injuries are particularly terrifying. A concussion or skull fracture inside a spacesuit helmet could cause swelling that's exacerbated by the suit's pressure. You might need to remove the helmet to address the injury, but you can't do that outside. Getting someone with a serious head injury back to the habitat safely, then treating them with limited neurological expertise and equipment, is a nightmare scenario with high mortality risk. Burns from equipment malfunctions or fires are another serious concern. In a pressurized, oxygen-rich environment, fires can spread rapidly. Burns require specialized treatment, including sterile dressings, pain management, and often skin grafts for severe cases. None of that is easily achievable on Mars. A crew member with severe burns would be in constant agony, at high risk of infection, and might face permanent disfigurement or disability with no real treatment options available. Let's talk about the spacecraft and habitat design philosophy, because it reveals just how dangerous Mars truly is. Engineers designing for Mars must assume that everything will eventually fail. It's called design for failure, and it means building in multiple redundancies, backup systems, and contingency plans for every critical component. But there's a limit to how much redundancy you can include before the mass becomes prohibitive and the complexity becomes unmanageable. Every system has what's called a single point of failure, a component whose failure causes the entire system to fail. Engineers work to eliminate these, but in complex spacecraft and habitats, they're sometimes unavoidable. Identifying and mitigating single points of failure is essential, but it requires exhaustive analysis and testing. Despite best efforts, unknown failure modes always exist, scenarios that nobody anticipated because they involve unusual combinations of problems occurring simultaneously. The more complex a system, the more potential failure modes it has. A Mars habitat would be extraordinarily complex, with thousands of interconnected systems, all needing to function continuously. The probability of something going wrong approaches certainty over a multi-year mission. The question isn't whether failures will occur, but how many, how severe, and whether the crew can recover from them. This brings us to crew selection and training, which might be the most critical factor determining mission success or failure. Who do you send to Mars? You need people with diverse skills: engineers, scientists, medical personnel, geologists, biologists, but they also need to be physically fit, psychologically resilient, able to work under extreme stress, capable of getting along with others in confined spaces for years, and willing to accept significant risks of death or permanent injury. The pool of candidates meeting all these criteria is extremely small. Then you need to consider team dynamics. The crew must work together effectively because interpersonal conflicts on Mars could be mission-ending. Psychological screening is essential, but humans are complex, and predicting how someone will respond to years of isolation and stress is difficult even with extensive testing. Training would need to cover an absurdly wide range of skills. Every crew member needs to know how to maintain and repair critical systems, perform medical procedures, conduct scientific research, operate vehicles and equipment, manage emergencies, and solve problems creatively with limited resources. The training program would likely take years and cost enormous amounts of money, all before a single rocket launches. There's also the question of backup crew members. In traditional space missions, backup crews train alongside prime crews, ready to step in if needed. For Mars, the training investment is so substantial that maintaining backup crews might be economically unfeasible. That means if a prime crew member becomes unavailable shortly before launch, there might not be a suitable replacement ready, potentially delaying the mission by years until the next favorable launch window. Launch windows to Mars occur approximately every 26 months when Earth and Mars are properly aligned. Miss your window and you wait over 2 years for the next one. This creates enormous pressure to launch on schedule, which might lead to accepting higher risks than ideal. The temptation to overlook problems, rush testing, or make compromises to meet a launch deadline could be strong, especially after investing billions of dollars and years of preparation. Let's examine the financial aspects because they reveal societal priorities and commitment levels. Estimates for the first human Mars mission range from $100 billion to $500 billion or more, depending on mission architecture and technology development needs. That's an almost incomprehensible amount of money, equivalent to the GDP of some countries, spent on sending a handful of people to another planet. For that investment, society deserves to ask difficult questions. What's the return on investment? Scientific knowledge, certainly. Inspiration and advancement of human capabilities, absolutely. But is it worth the cost compared to other uses of those resources? Could that money solve pressing problems on Earth? These aren't easy questions, and reasonable people disagree about the answers. The political commitment required is also substantial. Mars missions take decades from initial planning to execution. That spans multiple election cycles, changes in government leadership, and shifting public priorities. Maintaining consistent funding and political support over decades is incredibly challenging. The Apollo program succeeded partly because it had clear political motivation during the Cold War. What motivates a Mars mission today? Scientific curiosity and long-term species survival are important but perhaps less politically compelling than beating the Soviet Union to the moon. Private companies like SpaceX have proposed Mars missions with different cost structures and timelines. Commercial spaceflight has driven down launch costs significantly, making Mars missions more economically feasible. But private missions face their own challenges: shareholder pressure for returns, less regulatory oversight potentially increasing risks, and questions about who's responsible if something goes catastrophically wrong. There's also the question of mission objectives. Why are we going to Mars? If it's purely for exploration and science, robotic missions might provide better value. Robots don't need life support, don't get psychologically stressed, and can explore environments too dangerous for humans. If it's for eventual colonization, that's a multi-generational commitment requiring technologies we haven't developed yet. If it's for inspiration and advancing human capabilities, we need to honestly assess whether the benefits justify the costs and risks. Let's consider what colonization actually means, because popular depictions often gloss over the brutal realities. Establishing a permanent, self-sustaining colony on Mars would require not dozens but potentially thousands of people, enormous infrastructure, and technologies that don't currently exist. You'd need industrial-scale manufacturing, extensive agriculture, complete medical facilities, power generation far beyond what we've discussed, and the ability to produce everything locally that colonists need to survive. Think about what a self-sustaining colony requires. You need to manufacture spare parts, produce medication, generate construction materials, refine metals, create electronics, and eventually build new habitats and equipment entirely from Martian resources. This is industrial civilization on a planetary scale. Even small communities on Earth depend on global supply chains for countless items. Replicating that on Mars means building an entire industrial base from scratch on a world actively hostile to human life. The initial colonies would be completely dependent on supply missions from Earth for decades, possibly centuries. Every malfunction that can't be repaired locally, every resource that can't be produced on Mars, requires a shipment from Earth. Supply missions cost billions of dollars and take months to arrive. A colony couldn't just order emergency supplies overnight. They'd need to anticipate needs years in advance and hope nothing unexpected happens. Population genetics becomes a concern for permanent colonies. You need sufficient genetic diversity to avoid inbreeding problems over generations. Studies suggest a minimum founding population of several hundred individuals, possibly thousands, to maintain genetic health. Anything smaller risks genetic bottlenecks that increase the prevalence of genetic disorders and reduce the population's ability to adapt to new challenges. Reproduction on Mars presents entirely new questions that we have almost no data to answer. What does pregnancy look like in reduced gravity? How does radiation exposure affect fetal development? Can healthy babies be born and develop normally on Mars? These are critical questions for long-term colonization, and we simply don't know the answers. The first pregnancies on Mars would be experiments with enormous ethical implications. Studies on pregnant rats in microgravity have shown concerning results, including developmental abnormalities and difficulties with birth. Mars has some gravity which might mitigate these problems, but we won't know until humans try. That means some of the first children born on Mars might face health problems we can't predict or treat. They'd be pioneers in the most literal and frightening sense, their very existence an experiment. Children born on Mars would develop in reduced gravity with unknown consequences for their skeletal structure, muscle development, and organ systems. They might never be able to visit Earth because their bodies adapted to Martian gravity couldn't withstand Earth's stronger gravitational pull. They'd be Martians in a profound biological sense, humans who could never return to humanity's home world. That's simultaneously fascinating and deeply sad. Education and child development on Mars also raises unique challenges. Children need social interaction, play, exploration, and connection to nature for healthy psychological development. Mars offers none of the natural environments children evolved to thrive in. Growing up in habitats, unable to play freely outside, deprived of Earth's biodiversity and natural beauty, could have profound psychological effects that might not be apparent for years. Legal and governance questions for Mars colonies are equally complex. Who has authority on Mars? What laws apply? If someone commits a crime on Mars, who prosecutes them? What happens if colonies established by different nations or organizations come into conflict? We have international treaties about space, but they were written before permanent colonies were seriously considered and don't address many practical questions. The Outer Space Treaty of 1967 states that celestial bodies cannot be claimed by nations and should be used for peaceful purposes. But what does that mean for commercial mining operations or private colonies? Can companies claim resources? Can individuals own Martian land? These legal ambiguities need resolution before significant colonization efforts, or we risk conflicts and disputes that could turn ugly when there's no effective law enforcement millions of miles from Earth. Resource conflicts on Mars could be particularly dangerous because there's no higher authority to arbitrate disputes. If two colonies claim the same water-ice deposit, how is the conflict resolved? Diplomacy might work initially, but what if essential resources become scarce? The history of human colonization on Earth is filled with resource conflicts and violence. Would Mars be different, or would human nature reassert itself even on another planet? Environmental ethics also deserve consideration. Mars is pristine, untouched by human activity except for a handful of robotic landers and rovers. Do we have the right to fundamentally alter another planet? Some argue that Mars has no intrinsic value beyond what humans assign it, so using it for human benefit is justified. Others contend that we should protect Mars's environment, at least until we've thoroughly explored it and confirmed whether life ever existed there. Planetary protection protocols currently require sterilizing spacecraft to avoid contaminating Mars with Earth microbes. This is partly to preserve the scientific integrity of searching for Martian life, and partly out of environmental caution. Large-scale human presence would make contamination inevitable. Humans are walking ecosystems carrying trillions of microorganisms. Some would inevitably be released into the Martian environment despite precautions. What happens if Earth microbes find niches to survive on Mars? Could they spread, fundamentally altering the Martian environment in ways we can't predict? Some scientists worry about creating a biological catastrophe where Earth organisms outcompete any potential Martian life that might exist in subsurface environments. Others argue that Mars is so hostile that Earth microbes couldn't survive outside controlled habitats. We won't know until it happens. There's also the question of terraforming, deliberately altering Mars's environment to make it more Earth-like. Science fiction often portrays terraforming as a straightforward engineering project, but the reality is vastly more complex. Making Mars habitable without spacesuits would require thickening the atmosphere, warming the planet, and creating a magnetic field to protect from radiation. Each of these is a planetary-scale engineering challenge beyond our current capabilities. Proposals exist for releasing greenhouse gases to warm Mars, melting the polar ice caps to release water and carbon dioxide, and potentially importing volatiles from asteroids or comets. These processes would take centuries or millennia and require energy expenditures that dwarf anything humanity has ever attempted. Terraforming Mars isn't something the first few colonies could achieve. It's a multi-generational project that might not even be possible given Mars's fundamental characteristics. Mars has much lower mass than Earth, which is why it lost most of its original atmosphere. Even if we artificially thickened the atmosphere, it would gradually bleed away into space without a magnetic field to protect it. Generating a planetary magnetic field is speculative technology at best. Some propose placing a magnetic shield at Mars's L1 Lagrange point between Mars and the Sun, but this would require maintaining a massive artificial structure indefinitely. The engineering challenges are staggering. Even if terraforming succeeded, it would fundamentally alter Mars, destroying its current environment and any scientific information it holds about planetary evolution and the possibility of extinct or extant Martian life. Once you've terraformed Mars, you can never study pristine Mars again. That's an irreversible decision with profound implications for science and potentially for discovering whether life exists elsewhere in our solar system. Let's return to more immediate concerns and discuss sample return missions, because they illustrate the challenges facing even relatively simple Mars operations. NASA's Mars Sample Return mission, planned for the late 2020s or early 2030s, aims to bring Martian rock and soil samples back to Earth for detailed analysis. This mission architecture involves multiple launches, a Mars lander, a sample collection rover, an ascent vehicle, and an orbiter to rendezvous with the samples and return them to Earth. The complexity and cost of just returning a few kilograms of rock from Mars reveals how challenging the reverse journey would be for humans. If bringing back rocks requires a mission costing several $billion and years of development, imagine the scale of infrastructure needed to bring humans back. The ascent vehicle alone needs to be large enough to carry people, with life support systems functioning perfectly for the rendezvous and return journey. Sample return also raises planetary protection concerns in the reverse direction. What if Martian samples contain something hazardous to Earth's biosphere? The probability is extremely low but non-zero. Returned samples need to be quarantined and studied in biosafety level 4 facilities, the highest containment level used for dangerous pathogens. This adds complexity and cost, but is absolutely necessary to prevent even the remotest possibility of contaminating Earth with something from Mars. Returning astronauts would face similar quarantine requirements, possibly even more stringent than lunar astronauts experienced during Apollo. They'd need medical monitoring for potential exposure to unknown Martian biological or chemical hazards. Even if Mars is sterile, astronauts might bring back dust or compounds that could trigger allergic reactions or other health problems. The quarantine period could last weeks or months, adding to the already lengthy duration away from home. Now let's discuss what might be the most psychologically challenging aspect of Mars missions: the knowledge that you can't come home early. On the International Space Station, if a true emergency occurs, crew members can evacuate and return to Earth within hours using a Soyuz or Crew Dragon capsule. On Mars, there's no emergency return option. You're committed to staying until the planets align for a return trajectory, which happens approximately every 26 months.